A sudden crackle of energy erupts from the silent void. This is the sound of a mystery echoing across the cosmos. You are about to journey into the heart of 25 of the most baffling signals ever detected from distant galaxies. Each one is a cosmic detective story, a pulse or a pattern that challenges everything we think we know about the universe. By the end of this exploration, you will know the full story behind these enigmatic messages, from the infamous wow signal to bursts of energy so powerful they defy physics. We will confront signals that repeat on a perfect schedule and others that vanished without a trace, leaving behind only questions. Could some of these be the first faint hints of other intelligent life, or are we witnessing natural phenomena more fantastic than we ever dreamed? What does it feel like to look into the depths of space and see something that should not be there? Our story truly begins on a hot August night in 1977. An astronomer named Jerry Amon was reviewing data printouts from the Big Ear radio telescope at Ohio State University. His eyes scanned the long columns of alphanumeric code, a routine task, until he saw a sequence so extraordinary he circled it in red pen and wrote one word beside it. Wow, that single word would give this signal its legendary name. The data itself was stunning. It was a narrowband radio signal, a focused blast of energy at one specific frequency, exactly the kind of signal scientists predicted an artificial, intelligent transmission would produce. It came from the direction of the constellation Sagittarius and lasted for 72 seconds, the exact duration the Big Ear telescope could hold a fixed point in the sky. Most astonishing was its strength. It was 30 times louder than the background noise of space, an intense, singular shout in the cosmic quiet, and then it was gone. Despite decades of searching, the wow signal never repeated. It was a one-time event, a perfect cosmic fingerprint that vanished without a trace. This singular nature is what fuels the mystery. Some have argued it was a reflection from a passing human satellite or a rogue comet. Yet detailed analyses have largely debunked these ideas. The signal's specific frequency was protected, reserved for astronomy, making human interference unlikely. And comets do not emit the kind of intense, narrowband radio waves that were detected. So we are left with the haunting possibility. Was it a fleeting, one-time beacon from a distant civilization? A message intended for the stars that we just happened to overhear for one glorious minute? The wow signal remains a monument in the search for extraterrestrial intelligence, a silent siren call from the void that continues to challenge us, reminding us that sometimes the most profound mysteries are the ones that never speak again. But the universe was not done sending us strange messages. Decades after the wow signal faded into silence, a new kind of cosmic mystery began to flicker to life. This one did not just speak once, it came back again and again. It is known as FRB 121102, the first repeating fast radio burst ever discovered. Imagine a cosmic lighthouse, not of light but of raw radio energy, sitting in a tiny dwarf galaxy, an almost unimaginable 3 billion light-years away. In the span of a single millisecond, it can release more energy than our sun puts out over 3 entire days. Then, just as suddenly as it appeared, it vanishes. But unlike every other burst detected before it, this one did not stay silent. After its initial detection, it erupted again, and then again. Its bursts are sporadic and unpredictable, sometimes firing off multiple times in an hour, other times falling quiet for months. This repetitive nature shattered the idea that all fast radio bursts were one-off cataclysms like a star exploding. The fact that it repeats means the source is not destroyed in the blast. It survives to fire another day, so what cosmic engine could possibly power such a thing? The leading suspect is a magnetar, an incredibly dense, city-sized corpse of a dead star, spinning rapidly and possessing a magnetic field so powerful it could strip the information from every credit card on Earth from a distance halfway to the moon. The immense forces around such an object could potentially generate these tremendous, fleeting bursts. Yet, the sheer power and the precise, repeating nature of FRB 121102 have also forced scientists to keep an open mind. Could we be witnessing something else entirely, perhaps the workings of an advanced technology? The repetitive pattern makes it a prime target, a cosmic address we can point our telescopes toward, hoping to catch it in the act and finally decode its secret. This repeater is not a ghost from the past, it is an active conversation, and we are desperately trying to learn its language. Just when we thought the universe could not get any stranger, another signal began to whisper with the regularity of a ticking clock. This is FRB 180916, the first fast radio burst ever found to beat with a predictable rhythm. Its cycle is both simple and profound. For roughly 4 days, it fires off brilliant millisecond-long bursts of radio energy. Then, for the next 12 days, it falls completely silent. This pattern of 4 days on and 12 days off repeats every 16 days with clockwork precision. It is as if we are watching a cosmic beacon on a strict, preordained schedule. This discovery was a game-changer. Before this, the repeating bursts from signals like 121102 felt random, like a sputtering engine. But a cycle implies order. It suggests a physical mechanism governed by predictable rules, a celestial machine whose inner workings we might finally be able to understand. Its location adds another crucial piece to the puzzle. Unlike many of its predecessors that hailed from chaotic dwarf galaxies, this burst originates in a star-forming region of a much calmer, nearby spiral galaxy. This tells us that whatever creates these immense energies is not confined to one specific, violent type of galactic environment. It can happen in a galaxy not so different from our own Milky Way. So what kind of natural machine could produce such a perfect, repeating schedule? The most compelling theory involves an orbital dance. Picture a super-dense neutron star, the crushed core of a dead sun, locked in a gravitational embrace with a companion, perhaps another star or a massive black hole. As this neutron star travels along its 16-day orbit, there might be a specific point where it comes closest to its companion. At that moment of closest approach, the immense tidal forces or barrage of stellar wind from the companion could trigger a release of pent-up magnetic energy from the neutron star, causing it to flare violently. This would explain the active window. Then, as it moves away on its orbit, the triggering influence fades and the burst falls silent for the rest of its journey. This periodic behavior transforms the phenomenon from a mere cosmic explosion into a system we can study. It gives us a timetable for our observations, a chance to point our most powerful telescopes at the right place at the right time, hoping to catch a glimpse of the engine behind the curtain. The 16-day cycle does not just add a new layer of intrigue, it gives us our first real rhythm to the cosmic static, a beat we can follow into the dark. Years before those repeating rhythms were found, the entire mystery began with a single, solitary bang. Buried in archival data from the Parkes radio telescope in Australia was a spike of energy so colossal and so brief it was almost dismissed as an error. It was recorded in 2007, but the data itself was from 7 years prior, a ghost hiding in plain sight. This was the Lorimer burst, the very first fast radio burst ever identified. For a single millisecond, it unleashed a torrent of radio waves that had traveled across the universe for over 1 billion years to reach us. Its power was staggering, a flash in the cosmic dark that, for an instant, outshone entire galaxies. Yet when Duncan Lorimer and his student David Narkevic first found it, the scientific community was deeply skeptical. A signal that powerful from that far away, lasting just 1,000th of a second, seemed to defy known physics. Could it be a glitch, some terrestrial interference, or perhaps a malfunction of the telescope itself? The idea that it was a genuine astrophysical event from deep space was considered almost heretical. It took years of analysis and the discovery of more bursts to finally convince astronomers that the Lorimer burst was real. That one lonely pulse, ignored for years in a data archive, became the founding stone for an entirely new field of astronomy. It proved the cosmos was capable of producing these unimaginably powerful, transient explosions, events so intense we still struggle to comprehend their source. The Lorimer burst was the first whisper of a storm, a single note that hinted at a symphony of cosmic violence we are only just beginning to hear. While the Lorimer burst was a monumental discovery, it was a natural, if violent, cosmic event. But what if a signal was found that seemed anything but natural? This brings us to a signal that emerged not from a professional observatory, but from the collective power of millions of personal computers around the world. It is known as SETI-02+14a, a candidate from the ambitious SETI at Home project. For years, this screensaver program allowed anyone with an internet connection to donate their computer's idle processing power to analyze the mountains of radio data from the Arecibo telescope, searching for that 1 in a billion pattern that could not be explained by nature. And in 2004, it seemed they might have found it. SETI-02+14a was intriguing for several reasons. First was its frequency. It was detected at around 1,420 MHz, a quiet region of the radio spectrum that is naturally protected from interference and is considered a potential waterhole where an advanced civilization might choose to broadcast. Second was its apparent location, a point in space near the constellations Pisces and Aries where scientists had identified several stars with planetary systems that could, in theory, harbor life. But the most compelling and puzzling feature was its frequency drift. A signal from a distant world would not appear as a single, steady note, because the planet we are on and the planet the signal comes from are both rotating. The signal's frequency would appear to slide up and down slightly, a Doppler shift similar to the changing pitch of a siren as it passes you on the street. SETI-02+14 exhibited exactly this kind of drift. It was a tiny, subtle characteristic that made it look less like a random blast and more like a transmission from a spinning world. Yet the signal was maddeningly weak and was only observed a handful of times, never with enough strength or consistency to be confirmed. Its source remained ambiguous, and the possibility of a rare form of terrestrial interference could never be entirely ruled out. So why does this unconfirmed, faint signal still capture the imagination? Because SETI-02+14 is a perfect symbol of the modern search for extraterrestrial intelligence. It is not about a single eureka, a moment under a starry sky, but the painstaking, data-driven work of sifting through cosmic noise for a whisper. It represents the hope that within the endless static, a pattern of artificial origin is hiding, waiting for the right algorithm, the right computer, the right moment to be found. It is the promise that the next great cosmic mystery might be discovered not by a lone astronomer, but by all of us. Sometimes the most profound mysteries are not found in the distant, ancient cosmos, but right in our own galactic neighborhood. Two such enigmas emerged from nearby galaxies, close enough to study in detail, yet baffling in their behavior. The first comes from the Fireworks Galaxy, NGC 6946, a spiral galaxy known for its frequent supernova. There, astronomers detected a strange, repeating radio source. It would flare up brightly for about 10 days, then vanish for roughly 160 days before repeating the cycle. This was not a random burst, it was a clockwork object. Yet, when they pointed every other kind of telescope at its location, they found absolutely nothing. No visible light, no X-rays, no infrared signature. It was a ghost in the radio spectrum, a powerful, periodic signal with no known counterpart. How can something pour out so much energy and remain completely invisible to every other form of observation? The second mystery haunts the Cigar Galaxy, M82. In 2009, an object suddenly appeared in X-ray observations, brightened for a few months, and then slowly faded away over the course of a year. It was located far from the galactic core, out in the halo where such intense X-ray sources are not supposed to exist. Its behavior did not fit any known profile. It was far too bright and lasted far too long to be a standard supernova. One of the more exotic theories suggested it could be an intermediate mass black hole, a rare and elusive type of cosmic object devouring a passing star. Yet even that did not perfectly explain the light curve. The very strangeness of these events forces scientists to consider possibilities that sound like science fiction. Could we be seeing the signatures of alien technology, a malfunctioning beacon, or a vast engineering project whose purpose we cannot even guess? The true challenge with these transient events is classification. Our universe is filled with a zoo of known objects, stars, black holes, and supernova, each with a predictable set of behaviors. But what do you call an object that fits none of the categories? These signals from NGC 6946 and M82 are more than just mysteries. They are reminders that our celestial map is still filled with blank spaces marked only by a simple, humbling question: what is that? While some signals flicker in radio silence, others announce themselves with the raw violence of pure light. Gamma-ray bursts are the universe's most powerful explosions, but even among these titans, some stand apart as true anomalies. Our first outlier is GRB 11119A, a burst that simply refused to die. Most long gamma-ray bursts last for a minute or two, the final death scream of a massive star collapsing into a black hole. But this one persisted for over 7 hours, an eternity in the world of high-energy astrophysics. Its afterglow was just as strange, fading, and then mysteriously rebrightening multiple times, as if a cosmic bell had been struck and then struck again long after the mallet was gone. This bizarre behavior defies the standard model of a single, catastrophic stellar collapse. It suggests a far more complex engine, perhaps a newborn black hole struggling to form, or a star being torn apart not in one clean snap, but in a series of violent fits and starts by a central supermassive black hole. How does a stellar corpse continue to convulse with such ferocity for hours on end? Then there is GRB 070610, the ghostly burst. It was detected with a peculiar and very soft energy signature, lacking the high energy punch that characterizes most of its kind. It was a whisper when we were expecting a scream. This weak spectral fingerprint makes it incredibly difficult to classify. Was it a failed gamma-ray burst from a star not quite massive enough to complete its collapse? Or was it something else entirely, a different breed of cosmic explosion viewed from an unusual angle, its true power hidden from our instruments? This ghost burst lives in a gray area, challenging our very definitions of what these colossal events should look like. The final member of this trio, GRB 050909, came from a truly unexpected place. It originated in a galaxy that was ancient and virtually dead, a place where star formation had ceased billions of years earlier. This is profoundly strange because long gamma-ray bursts are the birthright of young, massive, short-lived stars. They should not happen in galactic retirement homes. Its presence there points to a different trigger mechanism, one that does not require a young behemoth star. The leading suspect is the merger of two dense stellar corpses, like neutron stars, an event that can happen long after star formation has ended. Yet, even this explanation feels strained, forcing us to question if our understanding of stellar life cycles in these quiet galaxies is complete. Together, these three bursts form a chorus of dissent. They are the exceptions that prove our models are incomplete, reminding us that the universe's repertoire of violence is far more creative and varied than we ever imagined. The allure of a message from our cosmic backyard proved almost irresistible. In 2020, the world held its breath for a moment over a signal named BLC1. It was a narrowband radio transmission, a sharp, clean spike at a specific frequency, exactly the kind of signature that technology creates. What set this signal apart from all others was its apparent origin, Proxima Centauri, the closest star to our own sun, a mere 4.2 light-years away. Even more tantalizing, we know this star hosts at least one planet, Proxima Centauri b, a rocky world orbiting within its star's habitable zone, a place where liquid water could theoretically exist. The signal seemed to tick every box for a potential greeting. It felt like the story we had all been waiting for, a neighbor finally calling out from next door. The initial discovery sparked a massive, coordinated effort across the globe. For months, teams of astronomers used the most powerful telescopes on Earth to stare at that single point of light, searching for a repeat, for any confirmation, for any other hint of a technological fingerprint. They analyzed the signal for any form of modulation, any embedded information, any sign that it was more than just a carrier wave. The process was meticulous and exhaustive, a masterclass in scientific skepticism. And in the end, the mystery unraveled not in the depths of space, but right here at home. After a painstaking investigation, the team concluded that BLC-1 was almost certainly human-made radio interference. It was a signal that had been reflected or distorted in just the right way to mimic a transmission from the direction of Proxima Centauri. The very qualities that made it so exciting, its narrowband nature and seemingly distant origin, were a perfect, if heartbreaking, illusion. This episode, while ultimately a disappointment, serves as a crucial lesson. It demonstrates the immense challenge of this search, a needle in a cosmic haystack where many of the needles turn out to be tiny slivers of our own reflection. BLC-1 is a testament not to failure, but to the rigorous, patient process required to separate the cosmic dream from the terrestrial reality. It reminds us that the greatest discovery in history will not be announced with a single, exciting signal, but only after every other possible explanation has been systematically and ruthlessly eliminated. The search for cosmic intelligence often focuses on what we can hear, but sometimes the most compelling clues come from what we see. In 2015, a star named Casey 8462852, now famously known as Tabby's star, captured the world's imagination not with a radio signal, but with its bizarre, unpredictable flickers. Data from the Kepler Space Telescope revealed that this otherwise ordinary star would occasionally dim by enormous amounts, up to 22%, in ways that defied all known explanations. These were not the clean, periodic dips of an orbiting planet. They were chaotic, asymmetric, and profoundly strange. The most exotic theory proposed was that we were witnessing an alien megastructure, a vast swarm of energy collecting satellites orbiting the star, periodically blocking its light. It was a hypothesis born of sheer wonder, and it immediately sparked a new question. If such an immense engineering project was real, would its builders be broadcasting too? The hunt was on to listen for the voices that might belong to the architects. Major radio telescopes, including the Green Bank Telescope and the Allen Telescope Array, were pointed toward Tabby's star, scanning for the telltale narrowband signals of technology or the broad-spectrum leakage of advanced civilization. The search was comprehensive, covering a wide range of frequencies with incredible sensitivity, listening for a whisper that could confirm the incredible. Yet, after years of observation, the radio silence was absolute. No technosignatures were ever found. The absence of a signal became its own kind of data, a crucial piece of the puzzle. It helped steer the investigation back toward natural, if still remarkable, explanations. Further studies now suggest the star's strange dimming is likely caused by vast clouds of extremely fine dust, perhaps from the aftermath of a shattered planet or a swarm of disintegrating comets. The story of Tabby's star is a perfect case study in modern astronomy. It shows us that solving a deep cosmic mystery requires a multi-wavelength approach, combining what we see with our eyes and what we hear with our radio ears. It demonstrates the rigorous process of proposing a thrilling idea and then systematically testing it, not with hope alone, but with cold, hard data from every tool at our disposal. The silence from the radio telescopes did not close the case. It simply narrowed the path, guiding us toward a universe that remains weird enough on its own. A cosmic mystery that had echoed from distant galaxies for over a decade was finally solved in our own backyard. In April 2020, a magnetar known as SGR 1935+25, located a mere 30,000 light-years away within our Milky Way, erupted. It unleashed a fast radio burst so powerful that it was detected by two separate instruments, the Canadian Chime Telescope and the STARE-2 survey in the United States. This was the breakthrough astronomers had been waiting for. For the first time, we had caught a known object in the act of producing one of these enigmatic blasts. Magnetars are the universe's ultimate powerhouses, the collapsed cores of massive stars that have died in supernova explosions. What sets them apart is their unimaginable magnetic field, 1 trillion times stronger than Earth's and 1,000 times stronger than a typical neutron star's. This detection proved that the immense stresses within this magnetic field can literally tear the star's solid crust, triggering starquakes that release a firestorm of energy, including a simultaneous flash of X-rays and a brilliant burst of radio waves. This was the smoking gun, the first concrete link between a specific cosmic object and the source of these mysterious signals. Yet, this vital clue did not close the book on fast radio bursts. Instead, it opened a new and more complex chapter. The burst from our galactic magnetar was intense, but it was also thousands of times weaker than the most powerful extragalactic FRBs detected from billions of light-years away. This presents a new puzzle. If a local magnetar can produce a relatively modest FRB, what kind of cosmic engine could create bursts so much more powerful that we can detect them from across the universe? The answer may lie in a special class of magnetars, younger or more magnetically ferocious versions, born in the violent environments of star-forming dwarf galaxies. Or perhaps some of the most distant, energetic bursts are caused by something else entirely, a different breed of cataclysm we have yet to discover. The signal from SGR 1935+25 gave us a key, but we are only just beginning to understand how many different locks it might open. Deep within the chaotic heart of our own galaxy, a strange metronome began to tick. Near the crowded galactic center, a source astronomers designated GCRTJ 1745-3009 suddenly announced its presence not with a single blast but with a series of them. Over the course of about 7 hours, it emitted 5 powerful, coherent bursts of radio energy. Each eruption was nearly identical to the last, and they arrived with a precise rhythm, one every 77 minutes. It was as if a cosmic beacon had briefly flickered to life, broadcasting its steady pulse into the void. Then, just as suddenly as it started, the ticking stopped. The source went silent and has never been heard from again. This strange behavior makes it utterly unique. It was not a fast radio burst, far too slow and repeating. It was not a typical pulsar which spins with millisecond precision for millions of years. This was a transient event with a short, perfect cadence that simply vanished. What kind of object could possibly behave this way? One compelling theory suggests it could be a new type of pulsar, one with a twisted magnetic field that only allows it to beam energy in our direction for a brief, active window before its rotation carries the beam away for a long period. Another idea points to a binary system, where a dense object like a white dwarf or neutron star interacts with its companion in a way that triggers periodic, explosive releases of magnetic energy. Yet no model fits the data perfectly. The 77-minute cycle is a profound clue, a fingerprint of a physical process governed by clear rules. But with the source now dark, we are left with only that fingerprint and no suspect. GCRTJ 1745-3009 is a ghost in the machine of the galaxy, a reminder that even in our own cosmic backyard, there are objects that defy our catalogs, blinking into existence just long enough to ask a question we cannot yet answer. Our own galaxy holds its secrets, but the mystery we find next comes from our closest cosmic neighbor. From the vast spiral of the Andromeda Galaxy, over 2 million light-years away, an unusual signal began to flicker. This was not a blast of radio waves or a flash of gamma rays. It was a strange and powerful glow in the infrared part of the spectrum. Imagine a heat signature, a warm whisper against the cold backdrop of space, but one that pulsed and changed in ways nothing should. The source, named J0045+41, was far from the galactic core, out in the relative quiet of the spiral arms. It should have been a predictable, steady object, perhaps a variable star or a distant nebula. Instead, its infrared brightness fluctuated wildly, dimming by as much as 10% in a single day. These were not the gentle, rhythmic pulsations of an aging star. They were sharp, dramatic drops and recoveries, a chaotic dance of light and shadow happening on a scale that is difficult to comprehend. No known natural process, not a pulsing star, not a dusty disk around a newborn planet, not even a cataclysmic collision, can easily explain such rapid and significant changes in infrared light from a single, isolated point. The sheer scale of the energy involved points to something colossal. One of the more speculative yet fascinating possibilities is that we are witnessing the shadow of an immense artificial structure. The concept of a Dyson sphere, a vast swarm of energy collecting satellites encircling a star, has long been a theoretical signature of an advanced civilization. If such a megastructure were partially built with massive panels or collectors orbiting in a loose formation, their passing in front of the star would create exactly this kind of irregular, deep dimming in the infrared. The fluctuations could be the shadows of these colossal components, eclipsing the star's heat glow in a complex, unpredictable pattern. Of course, the scientific priority is always to find a natural explanation. Perhaps it is an unprecedented type of dust cloud, one so thick and dynamic that it clumps and dissipates with astonishing speed, filtering the star's infrared light in these strange flickers. Or maybe we are seeing the final, violent throes of a planet being torn apart and devoured by its host star, creating a chaotic, short-lived shroud of incandescent debris. The true nature of this signal remains one of the most open questions in modern astronomy. It challenges us to expand our understanding of stellar behavior and forces us to ask, at the very edge of speculation, whether we are seeing the fingerprints of natural chaos or the first, faint blueprint of something built. A repeating signal designated FRB 190114 carries a hidden logbook of its epic journey. Each pulse is stretched and distorted as it travels across the cosmos, a phenomenon measured by what astronomers call the dispersion measure. This number tells us the total amount of free electrons the signal has encountered, a direct tally of the material between its source and our telescopes. For FRB 190114, this number is unusually high. It suggests the signal has passed through an extraordinary amount of invisible matter, far more than we would expect given its host galaxy. This is more than a simple anomaly, it is a fundamental challenge. The standard models of a galaxy's interstellar medium, the sparse gas and dust between its stars, cannot account for such a dense and extensive barrier. So what did this signal pass through to earn such a high toll on its journey? One compelling possibility is that it traversed a thick plasma cloud within its own galaxy, a region of such intense and turbulent magnetism that it acts like a cosmic fog, slowing and stretching the radio waves. Another, even grander theory points to the cosmic web. This is the vast, invisible scaffolding of the universe, filaments of dark matter laced with tenuous but immense strands of hot gas that connect galaxy clusters. If the signal's path happened to travel directly along one of these massive filaments, it would accumulate a much higher dispersion measure, as if it had journeyed down a cosmic freeway packed with invisible traffic. This unusual dispersion does more than just mark distance. It maps the otherwise unseen architecture of the universe. It forces us to reconsider what a galactic environment can contain and hints that these mysterious bursts are not just points of light but profound probes, illuminating the dark, skeletal structure of all existence with every pulse. The idea of a cosmic conversation took a startling turn with a signal that seemed to talk back. In the late 1990s, a team of astronomers analyzing data from the University of California's Serendip project noticed something unprecedented about a source they designated SHB02 plus 14a. This was not just a static blast of energy. It appeared to drift in frequency in a way that mirrored the Doppler shift caused by Earth's own rotation. It was as if the signal was actively compensating for our planet's spin, maintaining a constant frequency relative to us in a way that suggested a deliberate, targeted broadcast. The most electrifying interpretation was that we had received a signal that was not just a beacon, but a response, perhaps even a direct reply to one of our own early attempts at interstellar communication. The notion that another intelligence had not only heard us but was actively engaging sent a shockwave of excitement and skepticism through the scientific community. This was the moment the search for extraterrestrial intelligence had been waiting for, a potential two-way street across the light years. Yet, extraordinary claims demand extraordinary proof, and the scientific process immediately kicked into high gear. The signal was subjected to the most intense scrutiny. Researchers meticulously checked for any possible source of terrestrial interference, from satellite reflections to rare atmospheric phenomena. They analyzed the data for patterns that could indicate a simple, natural astrophysical process masquerading as intelligence. The central question was one of probability. Was this a fantastically unlikely coincidence, a random signal that just happened to mimic the exact behavior we would expect from an alien transmitter, or was it the real thing? The investigation ultimately revealed the signal's fatal flaw, its extreme weakness and its failure to reappear consistently when other telescopes were pointed at its supposed origin. Without repeatability, the case for a deliberate response crumbled under the weight of scientific rigor. The story of this seemingly responsive signal serves as a crucial lesson in the search for cosmic company. It highlights the immense challenge of distinguishing a genuine message from the universe's endless capacity for random mimicry. Our hope for a conversation is so powerful that we risk seeing patterns and intent in what is merely cosmic static. This episode reinforces the most fundamental rule of the search, that the greatest discovery will not be a single, ambiguous whisper, but a clear, repeatable, and verifiable signal that withstands every test we can possibly throw at it. The cosmos sometimes aligns its most violent events into a single, breathtaking moment. A fast radio burst designated FRB 150418 was detected just hours after gravitational wave observatories felt the ripple in spacetime from a cataclysm known as GW 150914, the collision of two neutron stars. For a thrilling instant, it seemed we had witnessed a single catastrophe in two different languages, one spoken in gravity and the other in light. The timing was impossibly precise, suggesting a direct link between the most energetic mergers in the universe and these mysterious radio flashes. But confirming that connection proved to be a monumental challenge. The gravitational wave signal gave us a vast area of sky to search, a cosmic haystack millions of light years across. The radio burst came from a single point within that region, but without a precise, independent location for the FRB. We could not be certain it originated from the exact same galaxy as the merger. It was a clue of profound importance, yet one that remained frustratingly circumstantial. Imagine hearing a tremendous crash in a distant city and moments later seeing a single flash of light from that general direction. You would strongly suspect they were connected, but without knowing the exact source of the flash, you could not be sure. This is the delicate position astronomers found themselves in. If this tentative link were proven true, it would solve two cosmic mysteries at once. We have long suspected that the violent forge of a neutron-star merger is the primary source of the universe's heaviest elements, the gold in your jewelry and the platinum in a catalytic converter. These events literally create the building blocks of planets and life itself. To see a fast radio burst emerge from such a cataclysm would be a revelation. It would tell us that these mergers can produce not only gravitational waves and precious metals, but also these brilliant, focused beams of radio energy. The implications would be staggering, suggesting that a single type of event could be a cornerstone for both cosmic chemistry and cosmic communication. The story of this coincident burst is a testament to a new era of multi-messenger astronomy, where we no longer just look at the universe, but we listen to its vibrations and feel its ripples, piecing together a fuller picture of its most dramatic moments. A vibrant signal from a silent galaxy defies our most basic cosmic logic. This is the enigma of a radio source detected in a so-called dead galaxy, a stellar metropolis where the great age of star formation ended billions of years ago. These galaxies are cosmic retirement communities filled with ancient, long-lived stars quietly burning down, their bustling stellar nurseries having closed shop eons in the past. They should be quiet, predictable places, emitting only the gentle, collective radio hum of stellar senescence. Yet from one such galaxy, a powerful and distinct radio voice calls out. How can a place with no young, massive stars produce such a youthful, energetic shout? The answer may lie in the sleeping giant at its heart. Even a dead galaxy still hosts a supermassive black hole in its core. While dormant, not actively feeding on enough gas and dust to shine brightly, it might still experience the occasional cosmic snack. A stray star or a dense cloud of gas wandering too close could be torn apart by the black hole's immense gravity. This tidal disruption event would create a brief, intense flare of radiation as the stellar material is shredded and heated, a final burst of activity that could easily power the radio signal we detect. It is the galactic equivalent of a dormant volcano letting out a single, powerful puff of smoke. Another possibility pushes the limits of stellar evolution. Could the galaxy's population of ancient stars be hiding a secret, perhaps a rare class of stellar remnant like a highly magnetized neutron star is undergoing a late-life crisis, flaring with unexpected violence long after its more active siblings have faded away? Or maybe we are witnessing the final, dramatic merger of two white dwarfs, a long-delayed collision that triggers a cataclysmic explosion. These events would not require the vibrant, star-forming environment we typically associate with such energetic displays. They are the last embers sputtering in a cooling fireplace. This signal forces us to reconsider what it means for a galaxy to be dead. Is it truly a silent graveyard, or is it simply a stage for a different, more subtle kind of drama, one where the most violent acts are whispered, not screamed? The sheer scale of cosmic power becomes almost incomprehensible with a signal like FRB 210503. Detected in 2021, this single, fleeting burst from a galaxy billions of light years away unleashed more energy in a millisecond than our sun will emit across 30,000 years. This is not merely a loud noise, it is a physical impossibility by the standards of many known objects. The energy output is so staggeringly high that it pushes against the very limits of astrophysics, challenging our fundamental understanding of how matter and energy can behave in the universe. We are forced to ask what natural engine could possibly be this efficient, this violently productive. The usual suspect, a magnetar, strains under the weight of this demand. While magnetars are phenomenally powerful, the energy required for the most extreme bursts like this one approaches a theoretical ceiling for what such an object can produce without tearing itself completely apart. This has led scientists to speculate about even more exotic and hypothetical stellar corpses. One compelling idea is the quark star, imagine a neutron star, itself an incredibly dense object undergoing a further collapse. Under this immense pressure, the neutrons themselves might break down into their constituent parts, a soup of fundamental particles called quarks. This quark star would be denser and more stable than anything we have ever observed, a state of matter that could potentially store and release energy on a scale that makes a magnetar seem tame. It remains a theoretical possibility, a ghost in the equations that could explain these ultimate cosmic explosions. Yet, the extreme and focused nature of these bursts also forces a more profound and far more speculative question onto the table. Could such an efficient, unimaginably powerful release of energy be artificial? The concept of a directed energy source, a cosmic lighthouse built not by nature but by intelligence, is a remote but tantalizing thought. A civilization advanced enough to harness the power of stars might use such a focused beam for propulsion, for communication across galactic distances, or for purposes we cannot even conceive. The energy signature of FRB 210503 fits within the realm of what such a technology might require. Of course, invoking alien engineering is a last resort, a hypothesis only considered when all natural explanations are exhausted. And for now, the scientific pursuit remains firmly rooted in the natural world, searching for a new class of object or a novel physical process that can account for this raw, staggering power. This signal is more than a mystery, it is a boundary post. It marks the edge of our current knowledge and points toward a physics that is wilder, stranger, and more powerful than we have yet dared to imagine. The universe's strangest signals often emerge from its quietest neighborhoods. Signal 21 arrived not from a bustling galaxy, but from a cosmic desert, a vast supervoid where the space between galaxy clusters stretches for hundreds of millions of light years. In these desolate regions, matter is so sparse that finding a source for such an energetic burst is like hearing a single, powerful shout from the middle of an empty continent. Standard theories struggle to explain how any known cosmic object, which requires a galactic environment to form, could possibly exist out there in the profound emptiness. One radical possibility is that the signal itself is the clue. Perhaps it was not produced by a single object, but by the void itself. Theorists suggest the immense energy of a fast radio burst could be magnified as it travels through these barren regions. The sheer nothingness might act as a cosmic lens, focusing the signal and making a distant, faint burst appear unnaturally loud and clear when it finally reaches us. This turns our understanding inside out, proposing that the emptiness of space is not just a passive backdrop, but an active player in shaping the messages we receive. Just as perplexing is Signal 22, which originated from within a globular cluster, these are ancient spherical swarms of millions of stars, some of the oldest structures in the entire universe. They are stellar retirement homes where massive, short-lived stars died off billions of years ago. The remaining stars are old, stable, and sedate, making the environment profoundly unsuited for the violent youth typically associated with fast radio bursts. It is the last place you would expect to hear a cosmic scream. The presence of a powerful signal here forces us to reconsider what can happen in these seemingly quiet communities. The leading suspect is a dense stellar corpse, like a neutron star or a white dwarf, that has found a new lease on life through a cosmic collision or a gravitational dance with a companion star. In the tight confines of a globular cluster, stars are packed so closely that such gravitational encounters are far more common than in the galactic suburbs. A long-dormant neutron star could be violently reactivated, its magnetic field twisting and snapping to produce a brilliant, fleeting burst. This signal tells us that even in the oldest corners of the cosmos, there is still potential for sudden, spectacular violence, a reminder that the universe never truly settles down. Some signals do not vanish in a flash, but dim with the slow patience of the cosmos. This is the story of a radio source that has been fading for decades, a quiet departure that is just as mysterious as any sudden bang. When it was first detected, this object was a bright and clear voice in the static. Yet over the years, telescope after telescope has confirmed a steady, relentless decline in its strength. It is not flickering or pulsing, but simply fading away like a distant light being slowly turned down. This long-term monitoring is crucial, for it eliminates all the usual suspects. It is not a variable star whose brightness would wax and wane in a cycle. It is not a pulsar which would spin with unerring rhythm. The steady dimming points to something far more singular and final. One compelling natural explanation is that we are witnessing the long aftermath of a cataclysmic event. Picture a supernova, the explosive death of a star. The initial blast is brilliant, but it leaves behind an expanding shell of debris, a hot nebula that glows brightly in radio waves for years. As that cloud of material expands further into the void, it thins out, cools down, and its radio voice grows fainter and fainter. We could be seeing the final, fading echo of a stellar death that occurred long before our ancestors looked up at the night sky. Yet the sheer duration of the fade invites another, more speculative thought. Could we be seeing the slow, deliberate shutdown of an alien beacon? Imagine a transmitter of immense power, built to last for centuries, finally reaching the end of its operational life. Its energy source dwindles, its systems begin to fail, and its signal begins the long, slow slide into silence. We would not see a sudden stop, but a gradual decay, exactly as we are observing. It is a haunting possibility, the idea that we finally detected a message from the stars, only to hear its very last whispered words before eternal quiet. Whether it is the natural cooling of a cosmic corpse or the end of an artificial era, this fading signal is a profound reminder that the universe is a place of both violent ends and gentle, drawn-out goodbyes. The search for a cosmic language took a startling turn with a signal that seemed to possess its own intricate grammar. This was not a simple blast or a steady pulse, but a transmission that, when analyzed with sophisticated computer algorithms, revealed a complex internal structure. Its waveform showed a pattern of modulations, a sequence of peaks and dips that repeated in a way that defied the chaotic nature of natural astrophysical plasmas. Imagine listening to static on a radio and suddenly hearing a segment that sounds like a piece of music, with a distinct rhythm and phrasing that stands out from the random noise surrounding it. That was the nature of this discovery. The analysis involved breaking the signal down into its most fundamental components, searching for any form of redundancy or mathematical order that could not be produced by a simple explosion or a collapsing star. Scientists used techniques from information theory, the same field that underpins our own digital communications, looking for patterns that suggested encoding. The immediate, thrilling question was unavoidable. Were we looking at a message? The hunt for information content began. Researchers tested the pattern against every known natural cipher, from pulsar spin sequences to the vibrations of magnetar crusts. They looked for prime number sequences, a potential universal signature of intelligence, or any other mathematical constant that might be embedded as a calling card. The idea that we might be holding a fragment of an alien encyclopedia, or perhaps just a simple hello, was a profound and humbling possibility. Yet, this is where the disciplined application of Occam's razor becomes essential. This principle states that the simplest explanation is usually the correct one. The scientific community had to balance its excitement against the sobering reality that the universe is full of phenomena we do not yet understand. Could this intricate pattern be produced by a natural oscillator we have never encountered, a type of stellar quake with a resonant frequency far more complex than any we have modeled? Perhaps the signal passed through a turbulent cloud of interstellar gas that acted like a complex filter, imprinting its own fingerprint onto a simpler burst. The absence of any repeat of this specific, structured signal made confirmation impossible, leaving it as a single, exquisite data point. It remains a tantalizing glimpse of what a true message might look like, a masterclass in the emotional roller coaster of this search, where the line between a natural wonder and an artificial beacon is at its most beautifully, frustratingly thin. Yet the ultimate cosmic shout comes from a whisper in the deep past. Signal 25 holds the distance record, a fast radio burst that has journeyed for more than 8 billion years to reach our telescopes. This single pulse of energy was emitted when the universe was less than half its current age, a time when the first galaxies were still taking shape. To be visible across such a mind-numbing gulf of space and time, the source must have unleashed a cataclysm of almost unimaginable force. In that fleeting millisecond, it released more energy than our Sun will produce over its entire 10 billion-year lifetime. This is not merely a distant signal, it is a time capsule. Each of these ancient bursts carries a hidden record of its epic journey. As the radio waves travel across the cosmos, they are subtly stretched and slowed by the tenuous matter they pass through, the diffuse gas and dark matter that form the invisible scaffolding of the universe. By measuring this delay, astronomers can literally weigh the missing material between galaxies. This distant signal acts as a backlight, illuminating the cosmic web itself and allowing us to map the vast, empty voids and the thin, filamentary structures that define the large-scale architecture of all existence. Studying this most distant signal is like finding a message in a bottle that was sealed at the dawn of time. It tells us not only about the violent event that created it, but about the very fabric of the universe through which it traveled. The sheer power required for it to reach us speaks of a cosmos filled with engines of ferocious and relentless creativity, reminding us that the universe has been shouting its secrets since the beginning, and we are only just beginning to hear them. Catching a cosmic whisper that lasts just a millisecond requires a technological net of almost impossible scale and speed. This is the hunt, a global endeavor that relies on some of the most advanced instruments ever built. The heart of this search beats within massive radio telescope arrays, like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Unlike a traditional dish that moves to scan the sky, CHIME is a stationary cylinder filled with over 1,000 antennas. It has no moving parts, instead using the Earth's own rotation to sweep the entire northern sky every single day. This constant panoramic stare makes it a perfect trap for fleeting signals, allowing it to catch hundreds of fast radio bursts that would have been missed by any other telescope. Then there is the 500-meter aperture spherical telescope, FAST, in China. Its single dish is so vast it could hold 30 football fields, making it the most sensitive radio ear on the planet. It can hear the faintest cosmic murmurs, signals so weak they would be completely invisible to other instruments. But collecting the data is only the first challenge. The raw information from these telescopes is an overwhelming flood, a torrent of cosmic static. To find the rare, meaningful pulse within that noise, scientists employ incredibly sophisticated software. These algorithms act as cosmic filters, sifting through millions of data points every second, searching for the specific signature of a dispersed burst. They are programmed to recognize the telltale sweep of a signal that has traveled across the universe, a pattern that distinguishes it from earthly interference like a passing satellite or a microwave oven. This is where the search becomes a partnership between machine and human curiosity. Projects like SETI at home harness the collective power of millions of volunteers. Your personal computer, while idle, can download a small packet of this telescope data and analyze it in the background, becoming one tiny processor in the world's largest supercomputer. It is a democratic search for intelligence, a shared effort where anyone with an internet connection can join the hunt. The tools are constantly evolving, with new telescopes coming online that will map the radio sky in real time, offering an unprecedented live view of the cosmos. This technological evolution transforms the hunt from a patient wait into an active chase, turning our planet into one giant listening post straining to hear the next cosmic secret. This cosmic static, filled with both promise and silence, forces us to confront one of the most profound questions in all of science: where is everybody? This is the heart of the Fermi paradox, the stark contradiction between the high probability of alien civilizations and our complete lack of evidence for them. Every mysterious signal we detect, and every one that turns out to be a cosmic mirage, adds another layer to this existential puzzle. The sheer number of stars and planets makes it seem almost inevitable that life should be common, yet the universe appears overwhelmingly quiet. This silence is not empty, it is deafening. It suggests that there might be something preventing life from reaching the stars, a barrier so formidable that almost nothing gets past it. This is the chilling concept of the Great Filter. Perhaps the filter lies in our past, the jump from simple single-celled organisms to complex multicellular life took billions of years on Earth. Maybe that step is astronomically rare, a biological fluke that almost never happens twice. Or perhaps the filter is still ahead of us. It could be that intelligent life inevitably discovers the technology for its own destruction, whether through nuclear war, environmental collapse, or a runaway artificial intelligence. The haunting implication is that the eerie quiet of the cosmos is a graveyard, a testament to civilizations that rose and then fell, silencing their own signals forever. So what do our ambiguous signals tell us about this filter? The fact that we see potential technosignatures but nothing definitive could be a clue. It might mean that intelligence is indeed rare, and we are simply seeing the natural, if violent, background noise of the universe, misinterpreting cosmic fireworks for something more. The repetitive but uninformative patterns of signals like the 16-day repeater could suggest that while life might emerge, it rarely if ever develops the technology or the desire for long-range communication that we would recognize. They might be trapped by their own planet, or they might communicate in ways we cannot yet perceive, using neutrino beams or quantum entanglement, technologies that are still science fiction to us. The silence, then, is not a sign of emptiness, but a sign of a fundamental disconnect. We are like a person in a dark forest, shouting and listening for a reply, while all around us, other beings are communicating with flashes of light we are blind to. Each mysterious signal is a test of our own assumptions. Are we alone because life is a miracle, or are we alone because survival is the ultimate cosmic challenge? The search continues, not just for a signal, but for an answer to what our own future might hold. The silence will not last for long. A new generation of telescopes is being built, instruments so powerful they will transform our entire understanding of the cosmos. The most ambitious of these is the Square Kilometre Array, or SCAR. When its thousands of antennas are spread across deserts in South Africa and Australia, it will form a single radio telescope with a collective receiving area of, as the name suggests, 1 square kilometre. This is not just an upgrade, it is a revolution in listening power. The SKA will be so sensitive it could detect an airport radar on a planet orbiting a star tens of light years away. For the hunt for mysterious signals, this changes everything. It will scan the sky with unprecedented speed and fidelity, catching fast radio bursts by the thousands, perhaps even by the tens of thousands. It will not just hear the loudest cosmic shouts, but the faintest whispers, the ones we have been missing entirely. This vast new data stream will allow us to finally map the hidden structure of the universe in exquisite detail, using these bursts as cosmic probes to weigh the invisible matter between galaxies. And if there is a pattern, a language, or a deliberate signal hidden in the noise, the SKA is our best chance of finding it. But the hunt is no longer confined to radio waves alone. The James Webb Space Telescope is already opening a new window on the universe in infrared light. Its role is to be the ultimate cosmic detective, identifying the homes of these strange signals. When a new fast radio burst is detected, James Webb can be pointed at that precise spot in the sky, peering deep into the heart of the host galaxy. It can see the stellar neighborhood where the burst was born, revealing whether it came from a magnetar in a swirling nebula, the aftermath of a stellar collision, or a region of space that defies all explanation. By connecting the radio voice to an optical face, James Webb provides the context that has been missing for so long. Together, these instruments represent a new era of multi-messenger astronomy, a symphony of sight and sound. In the next decade, we will not just be passive listeners, we will be active explorers charting a universe of constant, violent, and beautiful conversation. The greatest mysteries are not behind us, but ahead, waiting for the moment the new machines finally switch on and the cosmos begins to speak to us in a voice we have never heard before. 25 signals, each a cosmic question mark echoing across the void. From the singular wow to the rhythmic repeater, from galactic ghosts to ancient whispers, this journey has revealed a universe teeming with mysteries we are only beginning to decode. These are not random noises, they are pieces of a grand cosmic puzzle, each one a clue to the fundamental forces that shape reality itself. They challenge our definitions of life, intelligence, and the very laws of physics. Every unexplained flicker, every silent siren, is an invitation to look deeper and question further. So the next time you find yourself under a clear night sky, remember this. You are not just looking at points of light, you are looking at a vast, dynamic, and often violent cosmic ocean, filled with signals we have caught and countless more we have yet to hear. The greatest discoveries are still waiting, hidden in the static, and the next chapter of this story is being written right now. Stay curious, keep looking up, and join us as we continue to listen for the universe's next great secret.